All right, why don't we go ahead and get started. Thanks everybody for joining me today in our presentation suite. My name is Jesse Clayton. I'm the Director of Product for PCAI here at NVIDIA. I'm joined by my colleague Kedar, who was on hand to field any technical questions. Today, we're going to tell you about how to use NVIDIA NIM for building advanced AI workflows like digital humans and AI design pipelines. There's really three things that I'm going to talk about. First, I'm going to tell you about some of the trends that we're seeing in the AI space and challenges that we see being faced by AI developers and enthusiasts. Second, we'll tell you how you can use NVIDIA NIM to build some of these demanding AI workflows, and we'll deep dive into a couple of them. And then finally, I'll share with you technology and resources that you can use to start leveraging some of this tech into your own projects. I do want to mention one thing. I know that in the build listing, this was listed as a bring your own device lab. We're actually not going to be doing any active lab work in this as the presentation, but we'll be sharing information. You'll be able to use the materials that I share here later on if you want to start going through them on your own and integrating them into your own workflows. All right, so let's go ahead and get started. So first, I want to share with you NVIDIA's AI PC stack. The AI PC stack was really designed to deploy high-performance AI to a wide variety of use cases, and it represents a culmination of more than a decade of investment and research in AI technology that's now accessible anywhere from PC to data center to cloud. It all starts, of course, with the hardware. As you know, at the center of NVIDIA's platform is the GPU. You may know that RTX GPUs from NVIDIA feature tensor cores, which are dedicated AI accelerators that can be used to power your AI use cases. These RTX GPUs can be found in anywhere from thin to light laptops to powerful desktops and workstations, and they're really for on-device capabilities, demanding capabilities like graphics, like AI. Specifically for AI, you're going to be using them for running inference, for doing fine-tuning, for doing some training workflows. They're really good for rapidly prototyping and iterating with building this next generation of complex AI workflows. Now, we started integrating tensor cores into our RTX GPUs back in 2018 with the 20 series, RTX 20 series of GPUs. And we made this fundamental change to our architecture because we believed that there was going to be a need, going to be a demand to run AI on device in the future. And I think if you look around at the content of this conference today, that vision has largely been validated. And so that hardware, though, is only useful to the extent that developers can take advantage of it. And so on top of the hardware, we have libraries, we have models, we have SDKs and frameworks that they can leverage to get access to this really fast hardware. Starting with the acceleration libraries, first is CUDA and all the libraries that come along with CUDA. This is how you program a GPU like a general purpose computing device. And most developers won't actually use CUDA, they'll access it through one of the higher level libraries or frameworks. But if you need to really get down there and optimize something, that's always an option where you're basically programming on the middle directly. Next is TensorRT. This is our library for accelerated AI inference. You may have seen the announcement earlier this week that Windows ML, which was just recently announced, will be powered by TensorRT when you're running on RTX GPUs, so you'll get access to those really fast tensor cores for doing AI inference. And then finally, cuDNN is our library for doing AI training and AI fine-tuning. On top of that, NVIDIA builds a number of different models in different categories that are tailored to specific use cases or specific types of data, specific media. Starting on the left with DLSS, this is for increasing frame rates in video games and increasing visual fidelity in video games by using AI to generate the frames and the pixels in those video games. Optics is a library for denoising, a model for denoising ray trace content and 3D content. It's used in creator workflows. RTX video is used for stream videos to improve the quality of the video. Maxine is used in multimedia applications as well as augmented reality. Riva is used for audio streams, so processing voice, processing audio, generating audio. Nemotron is our generative AI library focused on language and LLMs. ACE is our set of models for animating 3D characters. And then, of course, we also optimize and accelerate the wide variety of community models or open source models that are out in the market. Now, we package these models, this technology, in different ways. So for ISVs, we have SDKs that encapsulate these models and other functionality. We also have plugins that give ISVs access to models running on the RTX GPUs that they can use for integrating into their platforms. Then for AI developers and enthusiasts, we have NVIDIA NIM. And NVIDIA NIM is a platform where we encapsulate AI models into containerized microservices that make it really easy to develop and deploy AI capabilities. And that's a lot of what we're going to be talking about in this presentation here today. And so this robust platform that addresses all of these different use cases has really driven fast adoption of AI technology running on RTX GPUs. And in fact, there are more than 750 AI-powered games and applications making use of this technology stack that you can download and use today that are accelerated by RTX GPUs. So you may ask, well, why would I run my AI locally in the first place? There's lots of great solutions for running AI in the cloud. And frankly speaking, for many use cases, AI running in the cloud is a good solution. It scales really well. You have access to lots of performance, and it's accessible from anywhere. But there are a number of reasons, a number of use cases where it's preferable to run the AI locally. And so what are some of those? Well, first, no server costs. If you have the compute on your device already, just use that compute for running the AI. Don't push it up to the cloud. It's always available, so if your internet connection is intermittent or you're not going to have an internet connection, then you don't have to depend on that if you have your AI running locally. Low latency. There are some applications like gaming and video that have latency tolerances on the order of milliseconds because you have to fit something within a frame, 60 frames per second or higher. And so for those, you need something that's running on device because you literally don't have time to go out to the cloud. Data privacy and locality. If your data already exists on your device, there's no reason to send it all the way up to the cloud just to run the AI and then download it again. That's silly. And then finally is high performance. So all these other reasons, these 4 reasons that I've said so far, this is really true for any local AI accelerator, whether it's an NPU or an integrated GPU or a discrete GPU. But high performance is what you get when you're on RTX, when you have a discrete, powerful GPU with dedicated AI capabilities. It's by far the fastest local AI accelerator. The latest RTX GPUs from NVIDIA, the RTX 5090, for instance, has up to 3,300 AI TOPS in performance. That's more than 50 times what you can get out of the highest performing NPU today. So, what would you do if you had access to more than 50 times performance running on your own device? And so, all of this is great, but who is actually running AI on RTX today? Well, it turns out a lot of people. There are more than 100 million RTX GPUs in the field today. So that's a pretty substantial install base if you're looking to deploy a new capability, a new project, a new AI workflow. And these 100 million RTX users are leveraging AI in all the things that I've talked about already, whether it's in gaming or content creation or productivity or other use cases. Now, despite that, we still see some challenges, especially when you're looking to spin up a new advanced AI workload, right? So some of the ones that I've mentioned before have already been integrated into SDKs, but when you're looking at it, what is the next thing I'm going to build? Well, you want to leverage a lot of different AI capabilities from different places, different models, and it's really difficult to bring all of that together. So let's just start from what does it take to get from a model that's sitting in Hugging Face to something that I can actually use with my workflow on device. Well, the first thing you have to do is find the right model. There's more than 1.2 million models in Hugging Face now. Finding the right one that's suitable for your needs can be a challenge. Next is converting the format. So this can mean quantizing it into a data type that's going to run and fit within the constraints of the device on which you're running it. And converting the model format into something that's going to be compatible with your AI backend of choice. Next is integrating with that backend itself. What do I mean by backend? Well, most of the models that you find in Hugging Face, by default, they're designed to work with PyTorch. PyTorch is great, it's really flexible, you can interleave Python code with it, but it's not the best performance. It doesn't deliver the highest performance. And so ideally you want to be working with the inference backend that is targeted for that specific hardware. But converting it into that backend can be a challenging process. Next is customization. So let's say you find a model that works generally well for the type of thing that you want to do, but you want it customized to your use case. And this could involve fine-tuning it on your data set. Let's say you're building a game character or some other kind of digital human, and you want to give it a specific personality. You want it to talk in a certain way. One way that you can achieve that is through fine-tuning the model. So that can be a challenge to do. Finally, libraries and glue code. So it turns out you can't just take a model and run the model and have it work. There's lots of libraries and glue code you need to put both before and after the model to convert data that you have coming in into a format that's suitable for the model, and then convert the output of the model into something that's usable in your workstream. For instance, if your model is taking images as input, well, you have to have the libraries that can read images and convert them into something that the model can use directly. And then finally, workflow integration. So you have this model, you have all your libraries, you have to connect those into an API or wire them to an API that's compatible with the ecosystem of AI tools that are out there on the market. So all of these little pieces are kind of happening in different places, but altogether this is a lot of friction, which really makes it challenging for AI developers and enthusiasts to leverage all of the innovation that's happening on the model side into something that they can actually build into workflows running on the PC. And so to address this challenge, back at CES, we launched NVIDIA NIM for RTX. So NVIDIA NIM is prepackaged microservices that are built into a container that make it really easy to get up and going quickly with AI workflows running on device. It's performance optimized with TensorRT, so I mentioned TensorRT is NVIDIA's backend for inference. They're prepackaged, they have all the libraries and everything that you need to run the model. You can just download them and get them going in one click. They run in WSL on your PC. They're compatible with the AI ecosystem of tools. That means that they use the standard APIs that have become kind of the de facto standards in the AI space. And I mentioned you can work on it on PC, but in fact, they're compatible with cloud as well. They can run in Linux, they can run in the data center. You can take the same container that's running in the data center, and if you have enough resources on device, you can run it on device and vice versa. This is really important. Let's say if you want to do your early development on device, and then once you've got it down to something you're ready to deploy into production, you want to put it in the cloud, then you can just push that same NIM into the data center and it works exactly the same. Or if you have a NIM that you're using in the data center because you've been experimenting with it, then you want to bring it onto your PC, you can just download it and run it on your PC. And this includes top models both from NVIDIA, like the ones that I mentioned before, as well as open source models from the community. So what actually goes into one of these containers? We'll just take a look over on the left-hand side of this diagram and do a deep dive. So it contains the AI model, of course. We've also quantized it using accuracy-aware quantization techniques. So it's smaller, it runs faster, and it maintains a good deal of the accuracy that the original base model has. You can fit larger models on your PC when you do quantization. Next, all the libraries and glue code that I mentioned. So we've taken all of the libraries that are necessary to run this model, the ones that go before and after the model in the processing pipeline, and integrated those into the container. Integrating them into the container is nice too, because then you don't have to worry about system interdependencies and dependency conflicts. So if you have two models and they each rely on a different version of Python, for instance, right? Those things are just a headache to deal with, to deconflict those and make sure you're using the right one. Packaging it all inside the container means you don't have to worry about that. I mentioned they're all wired into the standard APIs. So for example, if you're using a large language model, that's wired into the OpenAI chat API. So you can use it just like you're using ChatGPT, connect to the same endpoint. I mentioned this is all running on Windows subsystem for Linux. Again, that's really important because I think, as you know, AI research happens in Linux. And so all of the models, the model technology, the dependencies, those are all written first in Linux. By running in Windows subsystem for Linux, it means that we can leverage all of that, NVIDIA's entire AI stack, and easily deploy it onto device. And of course, this is all optimized on RTX GPUs. So let's take a look at one specific NIM to understand concretely what this means for how you're able to use it. This is the Flux model, Flux 1. It was just released recently, and it is an image generation model. On the left is the Flux model that you get out of Hugging Face. And these are images that are generated from the NIM and the one that you get in Hugging Face. And so the one on the left, when you get it out of Hugging Face, it's in FP16 format, floating point 16 format. And it's running in PyTorch. And so what that means is it's going to be larger, it's going to run more slowly, and it's going to be more difficult to deploy. So I mentioned the model. It turns out there's actually 4 different models because of the control nets that you need before you actually get to the image generator. And so pulling all those models and getting them all wired together can be a challenge. It takes more than 30 gigabytes of VRAM to run these 4 models together. So that really narrows the number of systems that you can actually run this on. And this is, we'll say, 1x performance. And just so you know what 1x means, this is on the order of 30 seconds to generate enough iterations to get this kind of an image. Now, if we look at the NIM for the Flux model, instead of 4 different models, it's just a single container that you can download and run. It takes only 13 gigabytes of VRAM, so now the number of systems that you can run it on is much larger, and it gets 3 times performance. So this is on the order of 10 seconds to generate that. Now, 30 seconds to 10 seconds may not seem like a big deal, but if your job is generating images, or you're an artist and you want to generate different ideas for the artwork that you're going to create, you can be much more productive when you're able to iterate rapidly with something that completes quickly. And so this can actually mean real money for somebody who has this as their job. Okay, so that's the Flux NIM. These are all of the models that we have released to date as NIM for RTX, and you can see they're for a wide variety of use cases. There's language models, LLMs. There are image models, like Flux that I just mentioned. We also just announced 2 new ones. There's the version 2 of Flux, which was just released, and the Flux Schnell, which is a faster version of Flux. Models for doing retrieval augmented generation. This is an embedding model. Models for doing speech recognition and for improving voice quality. Models for doing computer vision, and models for doing vision language. Now, having an individual model in a container is nice to get that model up and running quickly, but the real magic happens when you start connecting multiple models together to create complex AI workflows that can do more interesting, capable things. To help developers get started with doing this, we build what are called AI blueprints. And so these are developer reference projects that are built around NVIDIA NIM that show you how to take different NIM containers and wire them together into projects to do some of these workflows. So Chat RTX, you may be familiar with, is a chat app that uses RAG. It allows you to chat with your documents and your images. 3D guided Gen AI, we'll talk more in detail about this one in a minute, but it allows you to use 3D data to guide the content and the composition of an image that you're going to use AI to generate. And then finally, Project GAssist. So this is a blueprint that allows you to connect to an AI model that's running on your PC already and connect it to other platforms or frameworks so you can do things like tool calling or application assistant, those kinds of things. Now, I mentioned that NIM is compatible with an ecosystem of AI tools. And so these are all the tools that currently have support for NIM. So AI Toolkit for VS Code, LangChain, anything LLM, Langflow, Meta Crew AI. And I say Meta. Meta is actually a model partner, so we work with Meta. We also work with Mistral. We work with Black Forest Labs. To integrate their models into our NIM containers, right? So we have some models that are from NVIDIA, some models that are from our partners. And then, of course, Mistral I mentioned, and Flowwise AI. Also, with anything LLM with AI Toolkit for VS Code, you can get access to the models directly through their UI, right? So you can go in and select, hey, instead of using this model in Llama CPP, I'd like to pull a NIM from NVIDIA, and it'll actually to go and download the NIM for you directly, and you can use that as your AI within those tools. Comfy UI allows you to do that as well. Did I miss any, AC? Is that good? Yeah, okay, thanks. You can get access to all of this from build.nvidia.com. We have a QR code later in the presentation, but this is just a really easy one to remember. Now, this covers all AI, whether it's for data center or for RTX, and I'll show you how to navigate to the ones that are specifically for deploying on device. Okay, so let's take a deep dive now into one of these AI blueprints. So I mentioned the 3D guided generative AI blueprint. So as you know, image generation with AI has become very popular, both for enthusiasts and for artists. But one of the things that can be challenging with AI generated imagery is defining the composition that you want. So it's easy to describe the mood that you want and get some interesting results. But let's say you have a vision of, well, I've got this building over here and this fountain over here, and you want it to adhere to something like that. Doing that through prompting is very difficult, it turns out. It takes a lot of prompting to kind of get it to what you want to do. Instead, what you can do is use a 3D scene that you've created to guide the composition of the piece of AI art that you're generating. And so as an example, so we have a 3D generator coming in from Shutterstock, and actually this is powered by NIM in the cloud, so NIM works both on device and in cloud. From that, you get a 3D scene that you can import into Blender. You can export that 3D scene into Comfy UI, and then use that as input into the Flux NIM that we just talked about, and then use Flux to generate the content, the final content. So rather than me talk about it, let's take a look at a video of this in action.
Generative AI synthesizes amazing images from simple text prompts. Yet image composition can be challenging to control using only words. With NVIDIA NIM microservices, creators can use simple 3D objects to guide AI image generation. Let's see how a concept artist can use this technology to develop the look of a scene. They start by laying out 3D assets, created by hand or generated with AI. Then use an image generation NIM, such as Flux, to create a visual that adheres to the 3D scene. Add or move objects to refine the composition. Change camera angles to frame the perfect shot. Or reimagine the whole scene with a new prompt. Assisted by generative AI and NVIDIA NIM, an artist can quickly realize their vision.
Pretty cool, huh? So that shows you how an individual model, Flux, which is interesting by itself, once you pipe it into workflow, you can do some really innovative things. So the next one that we're going to look at and take a little bit deeper dive on is called Project R2X. So this is a digital human demo with NVIDIA NIM. If you've been by our booth, we have this running in the booth during certain times today. You can come check it out, see it in action. But this is an end-to-end workflow for combining a digital human, an avatar, with an AI backend. And so just to show you how this is architected, we have data coming in from the user that can go in through the microphone from the user talking. It can go in from the web camera, so what the web camera can see, and it can also come from the screen, so if you're building like an application assistant to help you with what's going on in the screen. All of that gets converted into embeddings and into context, which are then fed into a large language model. That large language model can be running in the cloud or it can be running on device. We're going to show you how you can run it on device here with an NVIDIA NIM. The output of that language model is converted into text. Of course, you have the output coming out as text. That gets converted into audio using a text-to-speech model. And then that audio is converted into audio to face. So it converts it into facial animations. That's integrated with the Unreal Engine renderer to produce the animated avatar at the end. So you can have a conversation with a 3D avatar that's powered by AI. So let's go through kind of what the challenges or what the design goals are for this project. So we want a real-time digital assistant with a 3D avatar. For this demo, for this project, we're going to have the main AI that's powering this, that is the large language model, running on device alongside graphics. So this is pretty demanding, right? You have 3D graphics and you have a large language model running side by side. Of course, we want it to be low latency and good throughput because we want it to be conversational. It's uncomfortable when you're speaking with someone or something where there's a lot of gap. And little to no coding required. Why is this important? Well, you want to try out something quickly. You want to iterate quickly. And you can go and code in details if you want later, but if you're just trying to try something out to see if it's even feasible and get a good working baseline, using a low code or a no code solution can be really effective. These are the steps that we're going to go through right now, and I'll walk you through what's happening in each one of these. You'll also be able to access this project when we release it in the coming weeks, so you can get access to all the code and everything. The first thing we're going to do is try NIM on the cloud. So all of the NIM containers that I showed you already, even before you download them, you can just go to our cloud and try them out to see how the models perform by themselves. Next thing you do is install the NIM on the PC. So you can do this through a Podman or Docker pull command, or you can use an installer to install it. Then you connect it into the processing pipeline. So I mentioned a low-code, no-code solution. We're going to use Langflow for this. If you haven't seen Langflow before, it's a really cool interface for building processing nodes that you can then connect together. You can get a lot done without really doing any or very little coding. It's pretty fun to use. And then finally, we'll connect it to our 3D avatar that'll be running in Unreal Engine. Okay? So for the first step, I'm just going to give you a quick tour of our build webpage. So if you go to build.nvidia.com, maybe you've already done this. This is what you see. And as I mentioned, these are all of the NIM microservices and blueprints and everything. We're going to look for ones that run on RTX. So from that list that I had showed you before. And to do that, I'm going to type in run on RTX here in the interface. And this gives me access, gives me a directory of those ones that I can run locally. So you can see there's the Flux model, Flux Schnell, which I mentioned earlier. There's some language models here like DeepSeek. Llama 3.1 is in here somewhere. Is this it here? Yeah, Llama 3.18b. And then we're going to take a look at Mistral Nemo 12b. So this is a model that NVIDIA has tuned based on the Mistral 12b checkpoint. And so if I click on this, I can go to a playground, which will allow me to use this online. So this is running in the cloud right now in NVIDIA's cloud, right? So I can ask things like, tell me, my hands are cold up here, so I'm having a hard time typing. Tell me what you can do, right? And so it gives me, a LLM description of what it can do. And so let's say I've tried a few of these models. I find the one that I want to use for my workflow. Well, my next step is going to be to download it. To do that, you would go to this deploy tab right here. And then Windows on RTX, so this will use WSL. And of course, you'll have to have WSL installed in order to use this. I mentioned you can also access through various tools. This is where you would, you can download those tools and get access to the models there. But I'll have to install WSL. Now, this can be kind of arduous for some people to do. Maybe you already have it installed, and so this isn't an issue for you. But if you don't, you can just run the simple installer here. It'll go set up all the prerequisites, pull everything that you need to get it running. It's just a really easy way to get started. Then you're going to come down and run the container. So I'm going to switch over back to the presentation where we have some embedded content for how to do this. And I'll just talk you through what's happening here. Okay. Are we playing? Yeah. Okay, so this is on the same page that I just showed you. Now we're going to do a podman run command, which is going to pull the container and run it the first time, which is also going to pull the profile that is appropriate for this GPU that I'm running on. So let's say you're running on a data center GPU, it's going to pull a different model profile than the one that's running on device. And differences might be that one's quantized more than the other one. Okay, so this is the output of that run command. And what it's doing is going through and pulling the contents of the container itself. And like I said, then it's going to run the container, which is going to pull the model, and it's also going to load the model into VRAM. So all this takes a little bit of time, but it's not too long. Okay, and so now the model is up and running, and the endpoint for this model is at this IP address right here. So that's the IP address that you would use when you're in WSL. Now that it's up and running, I'm going to also from WSL, I'm just going to run this curl command. So this is a really easy way to test to make sure it's running correctly. So it's going to send a query and then expect a response. So we copy that in a different terminal. And we get a response. Now, of course, it's all formatted as JSON. You wouldn't, in most cases, want the JSON output, but we'll show in a couple examples later what that looks like in natural text. And so just to show kind of side by side, you can see the terminal where we're running the container. You can see the responses from that. We're hitting the chat completion API. And then we get the response back. Okay, so really easy way to just pull everything you need to run the AI model quickly and then test it on device. So next, let's take the next step and actually write some Python code that we can use to work with the model. So this is just a really simple Python script. I mentioned that this is using the same API that you would use if you're using an OpenAI model. And so here we have Python code that is running the model in OpenAI ChatGPT 4.0. And so we'll ask a really easy developer question, like how do you tell if a Python object is an instance of a class? And just for fun, we'll ask it to formulate its response like a pirate, just because one does that kind of thing. So we run that. It's making the query to OpenAI, and here's the response that we get back. And so we're going to take the exact same code now, and the only thing we're going to change is the endpoint. So instead of pointing to OpenAI's endpoint, we're going to point to the local one for the NIM that we already installed and started running, right? So you can see this is the exact same code, exact same prompt. The only thing that's changed is this endpoint right here. Run that. I think we're going to run that. Sorry, I'm speaking a little bit ahead of the video. Okay, and we get a response back. So a couple things to notice here. The content is a little bit different. Well, that's because we're using a different model. Before we were using GPT 4.0. This is Mistral Nemo 12B. The content is still correct. It's just formulated differently because the models have been trained differently. They're different sizes. Second thing, you'll notice that the response came back really fast, right? So having that low latency, high performance on-device AI can be really useful for having low latency responses. Okay, so let's take the next step now. And we're going to start integrating it into our workflow. And so just noting that we have the NIM up and running here, and we're going to connect it into a LangChain workflow. So I mentioned before that Langflow. I mentioned before that Langflow is a really useful application for connecting processing pipelines, including AI, where you can wire things together using simple nodes. Just a quick tour of all the different templates that are available by default from Langflow, as well as some of the tools that you have access to for connecting into different workflows. So we're just going to start with the basic prompting template though, because we really don't need much to get this going. Okay, and so that comes with a system prompt that we can edit, the way that the chat input is going to get in, and then a connection to the LLM. So by default, it's connected to OpenAI, but we can change that, and we'll show you how to do that in a minute. There's also tools here that we can connect to, lots of different options. So first, we're just going to run it against the OpenAI backend. So we run the playground, and now it's just like we have a chatbot. We're just chatting with ChatGPT, basically, with GPT 4.0. Okay, so that's working. Now to switch that out, what we're going to do is we're going to delete this node, and we're going to replace it with the NIM node. In order to do that, we navigate to NVIDIA as the model choice or the model provider. It comes up with this node here, which has connection points that we can wire all of the other pieces to. So wire in the input, wire in the system prompt, connect the output. Okay, now we're going to run it, and it's actually going to fail. And the reason why it failed is by default, this is pointing to an API in the cloud, and we didn't provide the credentials for it. But we don't want one running in the cloud. In this case, we want it on the one that we've already stood up locally. So we're going to change that to the endpoint that we have running locally. Now the IP address here is different because now we're outside of WSL, we're in native Windows, and so we're connecting through the network connection from the native Windows into the VM running in WSL. And then we tell it which model that we're actually using. And now it's built. We can launch the playground. And now we're talking to the NIM that's running locally. So here we type, what can you do? I had asked this when we were talking to the instance in the cloud, and we get approximately the same response back. So next, let's start wiring this into our digital human. So this is Aki, and Aki is an avatar built with Unreal Engine and is powered by some technology from NVIDIA called NVIDIA ACE. So there's an NVIDIA ACE plugin that allows you to do interesting things, including animate the face. So if you have an audio stream coming in, that can be used to change the blend shapes that are on the avatar so that the facial expression or the shape of the face will match the audio stream that's coming out. This way you can have real-time conversations with text that's being generated dynamically. So by default, Aki also is connected to OpenAI. Let's just take a look at that. And in a minute, we'll show how to connect into our Langflow project. Now, Aki is just an avatar that we built. You can use the avatar builder in Unreal Engine. Oops.
Hello.
Hey, how's it going?
I'm good. How about you?
I'm all digital, so always at 100%. But thanks for asking. What can I help you with today?
What can you do?
I can help with all sorts of things, from giving tech tips, checking out YouTube video details, summarizing documents, to having a friendly chat. What do you need today?
Thank you.
You're welcome.
Okay, and so that was powered, again, just by GPT-4o. So now let's wire Aki into the workflow that we've built in Langflow.
Hey Aki, which model are you based on?
I'm based on OpenAI's advanced AI models. They keep me sharp and ready to chat about anything from the latest trends to just having a laugh. Let's keep it rolling.
Okay, so check to make sure that our NIM is still running. We'll stop the program, change the connection to point to our Langflow instance. And we're going to need to provide a flow ID. So each flow that you've launched within Langflow has its own ID, so you know which one you're connecting to. So to do that, we open up our R2X project that we had started before. We still have our Mistral Nemo 12B NIM selected, pointing to the right endpoint. One other cool thing that we can do in Langflow, I mentioned this a little bit earlier, is connect the workflow to different tools. And so here we're going to connect to Wikipedia so that Aki now has access to everything that's in Wikipedia for answering questions. Also to archive, so if we want to talk about research papers, she can be a source of information. So we wire all of these together. And if you have any questions about how all this works, I mentioned that we have Kedar here today. Kedar did all these videos and connected these things all together, so he can give you a detailed response. Okay, so there's archive. Okay, now everything's connected together. Let's run it, make sure it's working. Now we can publish it, and this is how we get the flow ID that I mentioned earlier. So we copy and paste the flow ID from this window into the R2X demo. And we run.
Hi there.
Hi Aki, how are you doing?
I'm doing great. Thanks for asking. How about you?
Hey Aki, can you tell me more about the Pike Place market from Wikipedia?
Pike Place Market is a historic public market in Seattle, Washington. Known for its fresh produce, local crafts, and vibrant atmosphere, it's also famous for the fish throwing tradition at the seafood stands. The market has a rich history and is a beloved destination for both tourists and locals.
When did it first open?
Pike Place Market first opened on August 17th, 1907.
That's pretty good, thank you.
You're welcome.
Can you use the archive tool to tell me more about the Q-LoRa paper? What does it do?
Q-LoRa is a technique for training large language models efficiently. It focuses on quantization methods that reduce the memory and computational requirements of training, allowing models to be fine-tuned more cost-effectively on less powerful hardware. This approach helps in making the training of large models more accessible and scalable.
What quantization levels are talked about in the paper?
The Q-LoRa paper discusses the use of 4-bit quantization. This quantization level helps in reducing the model's size and computational requirements while maintaining performance, making it suitable for efficient training and deployment on smaller hardware setups.
Okay. So that's the end-to-end workflow. In terms of how to get access to this, so we'll be releasing all this code in the upcoming weeks under Project R2X. That's an AI blueprint that you can leverage, which includes all of the AI processing as well as the digital human pieces, so you can connect them all together. This is just the avatar that we built. Aki, of course, this is in Unreal Engine's avatar builder, so you can build and connect any kind of avatar that you like. Okay, just some recaps here. So we built a digital human powered by LLM running locally on device. Again, you can take a look at a demo of this in our booth. NIM is delivering the quantized, optimized models for a conversational experience, really easy to stand up. Some learnings, you really need to select models that meet the accuracy requirements for the workflow. And so there are a lot of really small language models out there. Some of them aren't really that good for general purpose use cases. They hallucinate a lot. Sometimes they give responses that aren't even grammatically correct. And so having a model that's big enough to give you the level of accuracy that's actually useful in your workflow is really important. And to run those larger models, you need a device with larger compute capabilities, larger memory bandwidth. Complex AI workflows with multiple models and graphics require GPUs. So in general, running a single model, right, maybe you don't need a GPU for that, but when you get into these more demanding multi-model, multimodal use cases, that's when you really start to need the computational capabilities of an advanced AI processor like an RTX GPU. Some future steps, and you can actually see these in our booth. So enhanced interaction by connecting to the webcam. We actually have this hooked up in the booth you can look at. And then enhance the assistant capabilities by providing visibility to the display. So these are a number of ways that you can take next steps to start building more complex workflows out of this. Okay, so just to kind of tie everything together, developing with NVIDIA NIM and AI blueprints on RTX, you can start by experiencing the NIM on the web at build.nvidia.com. You can run them on your device by just clicking to install using NVIDIA's installer, download and install with one click. Leverage the AI blueprints that we've used as reference designs, so you can see how to integrate some of these workflows. Integrate those into agents using Langflow or other graph UIs, and then connect to a UI. So you can build these with NVIDIA's digital human. Again, we'll have the code for this accessible for you to make use of. So for next steps, you can explore and download NIM and AI blueprints at build.nvidia.com. There's a QR code you can use there. Or you can also join the NVIDIA RTX AI developer Discord. So a number of us are on that Discord. You can ask questions there, get answers both from NVIDIA folks and other folks in the community. And you'll also see the latest news there. So thanks very much for your time today. Happy to take any questions that anybody has.